Hey everybody. So the second lesson, we're going to deal with graphs of logarithmic functions. Now, this is going to be a little different because this is something you've really never dealt with before. Exponential functions, we never really dealt with them, but we sort of dealt with them. We've seen contexts where we've used them before. For a logarithmic function, this is going to feel very new to you. So part of today is just to get you comfortable with what these things look like and the relationship that they have to exponential functions. Okay, so to start with, what we're going to do is I want you to pause me in a second here, and you're going to try and draw on a grid the graph of y equals 10 to the x. Now that's an exponential function. We dealt with that in the last lesson. And label the y-intercepts and the horizontal asymptotes. Then try and graph the inverse of this. Now think about your knowledge of graphing inverses. Again, way back to unit 1 when we did transformations. An inverse, you can just take points that were on one graph, switch the x and y coordinates, and replot. So see if you can get a picture of that in your notes there. Say, okay, so pause me and try that. So what you should have seen there is you should have seen a picture that looked something like this. So the blue graph is y equals 10 to the x, and then this red graph is x equals 10 to the y. Remember, taking the inverse, we just switch x and y. So if y equals 10 to the x, the inverse of that would be x equals 10 to the y. Now, there's so many things we want to talk about here, but first of all, you would have graphed this mainly just by switching coordinate points. I want you to see that this is a reflection against the line y equals x. If I just kind of trace my mouse in there, you can see that it's being reflected against that line. And I want you to see that some of the characteristics for, well, actually all of the characteristics for the exponential graph, the blue one, essentially all the x characteristics become y characteristics in the red one, and all the y characteristics become x characteristics, because that's what an inverse does. So you've got this table that I was referring to that I'm hoping you've already filled out. The domain for y equals 10 to the x, the blue graph here, that was real. The range will be greater than 0. The x-intercept there isn't any because of the horizontal asymptote, and the y-intercept was at 0, 1. And then we had an asymptote, just like I said, at y equals 0. Now, for the red graph, x equals 10 to the y, the domain now becomes x is greater than 0, okay? Remember, that was from the range of the y equals 10 to the x. The range becomes a member of the reals. The x-intercept becomes 1, 0. The y-intercept, there isn't one because there's a vertical asymptote at x equals 0. Okay, so just double check that you've got all that filled in right, and then we'll keep going there. Okay, so the inverse of an exponential function is known as a logarithmic function, and you'll often hear us call it a log function. That's just short for logarithmic, okay? But that picture of that red graph that you just saw was a logarithmic function, and it is the inverse of the blue graph that you just saw, which was an exponential function. So the inverse of the exponential function y equals 10 to the x is x equals 10 to the y. That statement in and of itself, I already gave to you in the previous slide, and you should feel decently comfortable with that because all I've done is I've switched the x and y values. Now, this may feel a little weird. X equals 10 to the y can also be written in logarithmic form as y equals log base 10 of x. Now, we're going to do a whole lesson on how I did that later. That's not the point right now. What I need you to understand, and I purposely made both of these red, I need you to understand for me right now that this guy and this guy are the exact same thing, okay? They're two different forms of writing the exact same thing. That's all I need you to feel comfortable with at this precise moment. Okay, so how did that happen? Don't worry, we will learn how we switch to this new form from an exponential later on. For now, let's focus on the graph of logarithms and their transformations. If you know all the key characteristics of an exponential function, you know all of them for the associated logarithmic function as well. Just going back to that table that you just did, Remember that everything x switches to a y item and everything y switches to an x item. Okay, so while we do this together, I'm just going to put here kind of that base function of a log again. It looked like this, just because I want us to be able to refer to it, and this was the 0.10. Okay, so we're going to just kind of keep that in our head as we go through this. Okay, so we're going to apply transformation. So again, hopefully a lot of this is going to feel familiar. Consider y equals a log base 10 of b x minus h plus k. So what does a do? The a value represents the vertical stretch by a factor of a. How would this affect the key characteristics of the graph? Well, think about this. Take this graph that I've shown you here, and I want you to go like that to it, okay? If you go like that, all the y values are getting multiplied by a. Would it affect where the vertical asymptote is? No. Would it affect where this x-intercept is? No. Okay. It actually doesn't affect any of the characteristics at all when we stretch it out like that. What will happen though is it'll just look like it's going to grow quicker, because if the a value is greater than 1, I should say, but if I go like that, it's going to look like it's going to grow quicker. Okay. If the a value is a fraction, it would look like it was going to grow slower. But either way, it's affecting that rate of growth that we see. Okay, so it would not affect any of the key characteristics. It would, however, change the rate of growth. Okay, now the b value represents the horizontal stretch. And remember, that's a factor of 1 over b. How would that affect the key characteristics? So if I go back to here and I go like this, okay, if I go like this time it will affect several items. It's not going to affect the asymptote here because that's at x equals 0, and anything times 0 is still 0, but it will affect the x-intercept. And again, it will change how this looks like it's growing. So it'll change what that rate looks like. Okay, so the x-intercept and the rate of growth for that guy. The h value is the horizontal translation, so I'm moving it left or right. That will affect this asymptote, the vertical asymptote, and it will affect the x-intercept. So when I affect the asymptote, I now also affect the domain. It would affect the y-intercept as well. You can imagine right now there isn't a y-intercept here, but if I was to move this back a few units, suddenly I would have the y-intercept, right? Okay. The k value, I'm moving it up or down. So that's the vertical translation, and that would affect the x-intercept, okay? Moving it left or right and moving it up and down won't affect the overall rate of growth there, okay? All right, well, what if we change the value of the base? So what I want you to do is consider y equals log base 3 of x and y equals log base 1/3 of x. So I'm going to change the base, and I'm going to compare the base being a number greater than 1 and a number that's a fraction, some number that's between 0 and 1. Now, this is going to feel very similar to what we did yesterday with exponential graphs. I'm going to show you what these graphs are, but I'd love it if you tried yourself. So in order for you to try yourself, I have to give you a little bit of a lesson on where to get this button. So this works well if you are a Casio or if you're a new TI. If you are a Casio, you can press, if you're a gray Casio, you can just press F4, and then it's F2. It says log AB. If you are a white Casio, you can do the same thing. You just have to get to a few more buttons. So you'll press Option, and then Calc, and then more options, and then you'll see it as log AB. Now for those white Casios, you need to, it'll open up a bracket. It'll look like this. Log bracket, and you'll put whatever the base is here, and then comma, whatever the b value is there, okay, whatever the big number there is. So for log base 3 of x, a would be 3 and b would be your x, okay? If you are a new TI, you can press math and go up 2, and you're going to see log base there, and that will get you the same, same as the gray Casios, it'll get you a small little box that you can put the base in, and a bigger box that you can put the x, for this case, in, okay? So try and graph those and compare them. Pause me, see what you notice, And now on the next picture, I'll show you what the graphs look like. The graphs look like this. The pink graph is log base 3 of x, and the green graph is log base 1/3 of x. And what I want you to notice, just like with exponential functions, when that base value is greater than 1, I end up with a graph that's increasing. And when that base value is between 0 and 1, I end up with a graph that is decreasing. Okay. So what if we change the value of the base? Well, if b is greater than 1, now just a quick little conversation about that. We are not talking about that b there. This here is the standard b in an equation. It's not the b that's involved in transformations. Okay, so the standard equation would be log base b of whatever. Okay, so if b is greater than 1, the graph will be increasing. And if b is between 0 and 1, the graph will be decreasing. Okay. All right, so tell me the transformations. Well, the very first thing you're going to do is you're going to look at that and say, hey, I have to factor that. That 2 has to come out. And so that's going to be written as 3 times log base 10 of 2 bracket x plus 2, and then plus 6. So I've got a vertical stretch of 3 about the x-axis. I've got a horizontal stretch of 1/2 about the y-axis. I've got a horizontal translation, 2 units left, and a vertical translation, 6 units up. Okay. Now, determine the equation of the vertical asymptote. Well, the vertical asymptote would have been at x equals 0. I've now shifted that to the left, 2. So that's going to give me at x equals -2 now for a vertical asymptote. Explain whether the function is increasing or decreasing. This guy here would be increasing. And the reason I know that is because my b value here is greater than 1. You also want to think about your a value with logs, because you can imagine if a was negative, that would flip it vertically, and that would cause an increasing to become a decreasing. Okay, but a is positive here, b is greater than 1. This is for sure going to be a graph that is increasing. If I was to state the domain and range, well, think about it. I've taken this graph here and I've moved it back 2. So my domain is going to be greater than -2. I've moved it up 6, but my original range was real, so it's still going to be real. That doesn't matter. Okay, so I have a domain that goes from -2 to infinity, and a range that goes from -infinity to infinity. Okay, the second guy there, we're taking a look at 5 log base 10 of -1/6 x plus 12 plus 7. Okay, kind of a sneaky thing on us here, but I need you to see this -1/6 x right away. That has to be factored out, which means you're dividing by a fraction. Be very, very careful. A lot of kids are going to tell me that 12 divided by 1/6 is 2, because they're just thinking in their head 12 over 6. It's not 12 over 6, it's 12 over 1 over 6. Dividing by a fraction is the same as multiplying by its reciprocal. So that's really, when I divide that out, the same as saying 12 times -6. So that actually is going to change to a -72. So the -1/6 comes out, and I have x minus 72 in the brackets. So that gives me 1, 2, 3, 4, 5 statements you need to make for transformations. We're going to have a horizontal stretch of 6 about the y-axis. We're going to have a vertical stretch of 5 about the x-axis. We're going to have a horizontal reflection. We're going to have a horizontal translation 72 units right, and we're going to have a vertical translation 7 units up. So determine the equation of the vertical asymptote. We want to take a look at how we've moved it left or right. We've moved it 72 units to the right. So my equation will be x equals 72. Is this function increasing or decreasing? Well, the original one would have been increasing, right? My a value is positive, so that's not going to affect it. There's no reflection there. I do, though, have a negative b value. So I'm going to take this and I'm going to flip it. Well, if I take this and flip it, that's going to end up being a decreasing value now. So my base is still a positive 10. It's still greater than 1. But because that b value is negative, this function overall is going to end up being decreasing. Okay, so now we're going to state the domain and range. Well, let's deal with the domain first. We just said that I'm going to take this, I'm going to flip it. So now instead of a point to infinity, as soon as I flip that, that's going to end up being negative infinity to a point. So it's going to be negative infinity to 72 because I've moved it 72 units to the right. And then the range will still be real. Okay, cool. Now we're going to try and build some equations. Oh, let me get that ink off for you there. Sorry. Okay. So determine the equation of the following transformed function in the form y equals a log x. So the blue graph here is log x, and I want to use that to compare the red graph. Well, the first thing I want you to see is that the x-intercept has not changed. Okay, this x-intercept right here hasn't changed. Then I want you to see that the point the point 10, 1 has changed to the point 10, 5. Now, if the point 10, 1 is changed to the point 10, 5, 1 changed to 5. So that kind of tells us that there is a vertical stretch here of 5. So if that's the only thing I was looking for, right, it was only looking for us to add an a value in, we can write that as y equals 5 log x. Okay? Okay, and then the next one, we're throwing in an a value and an h value. But what you got to see is we're basing it off of this function here. And this function here actually already has that h value, and we're not moving it based on that h value. I know I'm not moving it from the -1 there, which actually is an h value of 1, just for clarification. I know I'm not moving it from there because the red one doesn't have a new asymptote. It's still right at the 1, and the x-intercepts are still the same. Okay, so really, this is very similar to the first question I just asked you. We're just trying to compare y values so we can see what that vertical stretch is. So for this guy, I have the 0.52, and the 0.52 turns into the 0.56. So if I have a 2 turning into a 6, that's going to tell me I've got a vertical stretch of 3. So I add in an a value there of 3. Okay, so now this was a released diploma item a couple years ago. The partial graph of the logarithmic function f of x equals a log base b of x minus h, where b is greater than 1, is shown below. So we've got that guy here. Now, to produce the graph of y equals f of x above, the a value and the h value in the function must satisfy what? So what I need you to see, first of all, is because this asymptote has been shifted to the right, that means h has to be positive. H being positive shifts me to the right. Remember, it's not about what it is in the equation right now. H itself is positive if I'm shifting to the right. In the equation, just like every transformation question you're asked, it'll say x minus whatever that number is, right? But h itself will have to be some sort of a positive number. Now, the regular logarithmic graph looks like this. In order for it to have looked like that, I had to have flipped that vertically. So my a value has to be negative. So my a value has to be negative, and my h value has to be positive, which means the answer in this particular question will be a. Okay, also a released diploma item, the graph of each logarithmic function listed below where b is greater than 0 has a vertical asymptote. How many of these functions listed have an asymptote that's at x equals 0? Well, let's go through them one by one and see. The first one I see is y equals log base b of x. There's actually not really any transformations applied to that, so that's going to look kind of just like this guy. And that does have a vertical asymptote at x equals 0, so I'm totally cool with that guy. If I vertically stretch this, which is what I've done in the next one, I've just thrown an a value of 2 there. If I vertically stretch that, that does not change that asymptote. So that also has a vertical asymptote at x equals 0. If I horizontally stretch it, well, normally a horizontal stretch would affect x values. And that vertical asymptote is x equals 0. But because it's x equals 0, anything times 0 is still 0. So that actually is still going to have a vertical asymptote at x equals 0. If I move it up 2, if I took this guy and moved it up 2, that has no effect on that vertical asymptote. So that as well will still have a vertical asymptote at x equals 0. The last guy, however, I've moved it to the left 2. Well, if I move this guy to the left 2, the vertical asymptote does move to the left 2. That one would have a vertical asymptote at -2, not at 0. And so my answer to this is 1, 2, 3, 4. 4 of them will still have an asymptote at x equals 0. Okay, and then the last question here, a student sketched the graphs of f of x equals log base a of x plus 3 minus 7, and g of x, equals a to the x minus 2 plus 5, where a is greater than 1, on a coordinate plane. She also drew in the asymptotes and the two graphs using dotted lines. The intersection point of the two dotted lines would be at, well, you have a logarithmic graph there for the very first one, where it has been moved 3 to the left and down 7. Now the down 7 is sort of inconsequential to us right now, but the moving 3 to the left is super important because the 3 to the left is going to cause that asymptote at x equals -3. Okay, so this graph might look something like this. Okay, I'm just drawing a sketch. Remember, it's been moved down 7. Might look something like that. Then the g of x is an exponential graph. An exponential graph has a horizontal asymptote at y equals 0, but then that's been moved up 5. So this is now going to have a horizontal asymptote at y equals 5. And then I'm going to have some sort of a exponential function there. So it might look something like this. Okay, doesn't matter. What matters is we were asked, where will these 2 points on the dotted lines, what point will those 2 dotted lines intersect at? And they intersect right there, which is the point -3, 5. Okay, -3, 5. So the answer to that guy would be B. Okay, so your homework has been posted here. You're going to go through that and connect with me if you have any questions. And then the next lesson, we're going to start looking at exponential equations and how to solve them. So hope everybody's doing good. As always, email me or come see me with any questions that you have. Take care, guys.